what if you could take one part of an impossibly complex calculation and make it so fast that it's basically free? Well, today we're going to break down a really brilliant AI breakthrough that does exactly that, pushing forward our ability to simulate some of the most extreme physics you can imagine. So, let's say you want to design the future of flight. We're talking next-gen spacecraft, hypersonic jets, that kind of thing. To do that, you have to predict how gases will behave under just incredible amounts of stress. Now, we've got the equations, we know the physics. The problem isn't the what, it's the how fast. Running these simulations, even on the world's most powerful supercomputers, can be an absolute crawl. We're talking hours, days, sometimes even weeks for a single run. The main tool scientists use for this is something called a Fokker-Planck simulation. All you really need to know is that it's a super detailed way to model every single particle in a gas. And you absolutely need that level of detail when you're dealing with the thin air of the upper atmosphere or the intense shock waves from something moving at hypersonic speeds.
Okay, so these simulations are incredibly powerful, but they have one huge problem. They are just so slow. So a team of researchers decided to go on a hunt to find the one specific part of the process that was grinding the whole thing to a halt.
If you look at the simulation, it's basically a loop. You move the particles, you calculate their properties, you figure out how their velocities are going to change, and then you hit this one step. It's called the closure problem. And yep, this is our culprit. And this is not a small problem. We're talking about a single step that can eat up a staggering 40% of the entire computing time. That is a massive bottleneck. It makes these critical simulations almost impractical if you want to do rapid design and testing. So what exactly is this problem? Well, at its heart, it's a massive, repetitive math equation. For every single point in the simulation and for every tiny step forward in time, the computer has to solve this really dense 9x9 linear system just to figure out what happens next. It's basically the computational equivalent of doing a really hard long division problem millions of times every second. Now, in our modern world, when you have a complex, repetitive problem, what's the first solution everybody thinks of? Artificial intelligence, right? So the obvious question is, can we just throw an AI at this thing and call it a day? And the initial plan seemed pretty straightforward. You train a deep neural network on tons of data from the original slow physics solver. The goal is to teach the AI to see the pattern and just predict the answer instantly. You'd completely bypass that expensive, time-consuming calculation. But this is where the story gets a really fascinating twist. Because that seemingly perfect AI solution, it introduced its own completely unexpected problem, a hidden trap that nearly derailed the entire project. So here's what happened. The main physics simulation, all the heavy lifting, runs on the superfast GPU, but a standard AI model runs on the CPU. This created a constant, sluggish traffic jam of data. The GPU would be working, then it would have to stop, send data over to the CPU for the AI to make a prediction, and then just wait to get the answer back. This communication delay was so bad, it actually made the fast AI solution slower than the original method. And this is what brings us to the real breakthrough. The researchers didn't just fix the new problem. They found a way to make the AI so incredibly efficient that its cost became, effectively, zero. Let's actually look at the quote directly from the research, because this is the key to everything. They said, "We extract the trained model's parameters and re-implement the entire neural network forward pass using pure GPU native matrix operations." Okay, so what does that actually mean? Well, instead of treating the AI like some separate, clunky program, they basically took it apart. They pulled out its core components, all the numbers it learned, its weights and biases, and they rebuilt it from scratch inside the GPU, using the GPU's own native language. The AI went from being a tourist, constantly asking for directions, to being a local who knew all the shortcuts. The data never had to leave the GPU, and the bottleneck just vanished. So, the big question is, did it work? Well, the researchers didn't just want to show that it was fast, they wanted to prove it was as fast as was theoretically possible. This was going to be a real mic drop moment. First things first, though, they had to make sure the AI was accurate, and this was a crucial step. It turned out an AI trained on simple 1D data just couldn't predict the complex temperature fields of a 2D simulation. But as soon as they trained it on the right kind of 2D data, boom, the result was a perfect match. Okay, so now they knew the AI could be trusted. Now for the proof of speed. For this, we need to quickly talk about something called Amdahl's law. Think of it as the ultimate speed limit in computing. It says that the maximum speed up you can get is always limited by the parts of the program you can't optimize. So if 50% of your code is impossible to speed up, you can never get more than a 2x speed up, even if you make the other half infinitely fast. It's a hard ceiling.
So let's look at the numbers. For their simulation, the unoptimizable parts meant that the theoretical maximum speedup, the hard ceiling from Amdahl's law, was 1.727 times. And what did their AI actually measure? 1.73x. They didn't just approach the speed limit, they smashed right through the finish line tape. It was basically a perfect result.
And what this means is just incredible. Their GPU-native AI was so perfectly optimized that it became zero cost. It was running so fast that its own runtime was completely hidden by the other parts of the simulation. They had achieved the absolute theoretical maximum performance.
And when they applied this exact same technique to an even more complex, more realistic problem, simulating hypersonic flow over a cylinder, the results were even more staggering. Because the closure problem was an even bigger bottleneck in that simulation, eliminating it resulted in an overall speedup of a massive 3.85 times.
So you see, this is so much more than just one clever trick. This really points to a whole new way of thinking about scientific computing and the incredible role AI can play when it's deeply integrated. Which leaves us with a final, really provocative thought. We've just seen how a perfectly integrated AI can make a computational bottleneck effectively vanish. So it makes you wonder, what other grand scientific challenges, from climate modeling to drug discovery, are stuck behind similar impossible problems that are now suddenly solvable?